we've talked about how the engine works. So now I want to talk about how we test to see if it's working properly. And that's really the crux. Knowing how something works and how to figure out what's not working or why it's not working is really the hard part. You know, how it works is nuts and bolts. How to figure out what's wrong, that tends to be a different story, because we don't want to just open it up, take it apart, and see what's there. We want to run external tests to see what's going on inside. So in other words, I shouldn't be taking apart an engine unless I already know what's wrong, or at least have narrowed it down to one or two things and I need to do disassembly to figure out which of those things is bad. So critical step in the diagnostic process for an engine to operate efficiently and effectively, to diagnose more accurately in what major engine work is needed, or if it's not needed, and to better advise customers on appropriate repairs and build credibility with them. So this is a lot of communication. If I tell you you need an engine and it's $5,000, you're probably going to want to know why I think it needs an engine. What's wrong? What happened? Why is it $5,000? Why can't we fix it for $2,000? Why can't we fix it for $200? Those are all questions that customers are going to have. And we get that information by doing a diagnostic and figuring out what's wrong, and then looking at the vehicle on a whole. So in other words, I might repair an engine differently on a car with 80,000 miles than on a car with 200,000 miles. An example would be maybe a blown head gasket. If I have a blown head gasket on a car with 80,000 miles, I will probably just do the head gasket repair and send the head out and have the head machine. If that same car has 200,000 miles on it, I know that bottom end of the engine is worn. It doesn't make sense to rebuild the top end of the engine when the bottom end has 200,000 miles on it. That's a bad investment for my customer to make. I'm going to look at replacing the whole engine. So same condition, same problem, but different recommendation based on the vehicle. There's other times we might do a diagnosis and look at the car and go, it's time to call ecology. This is done. You don't want to put any more money in this car. This car is done. It's got dents, broken windows, doors that don't open, a plethora of other problems, and it's finally dead. Time to go get a new car. Don't waste any more money on this. So that's really, again, same diagnosis, but what? A different recommendation to our customer. So we're going to explain how engine mechanical testing is part of the diagnostic process. Uses a series of tests to assess mechanical condition. First thing we want to do is verify the customer's concern. So this is a visual inspection. This is an interview with the customer. Did it overheat? Did it overheat and stop running? You said it overheated. What do you mean by overheat? It smelled warm. You saw steam coming out. There's stuff coming out the bottom. Was the oil light on? So we have questions we want to ask the customer. Did the check engine light come on? Did it come on before the car died or when the car died? So there's information that we want to get to help us better diagnose the vehicle. Then we need to research possible faults and gather information. So research can be a couple of different places. It could be on the vehicle, my visual inspection, putting a scan tool on it, pulling any codes that might be there, looking up what those likely cause of those codes are to better understand the system I'm working on, and then focus testing. Because remember, diagnosis is gathering information, coming up with a hypothesis, and then proving or disproving that hypothesis. One of the mistakes people make is they don't gather enough information before they start jumping in, or they think they know what's wrong. Kind of like always choosing A on a multiple guess test. If you're always jumping at A, you might not see the correct answer is all the above, or you might not realize you misread the question and it was all the following except. Afterwards, if the customer authorizes it, we would perform the repair. And the most important thing is you verify the repair. What verify the repair means is that I'm verifying that the system operates as designed after I've done the repair. A lot of times people will think something's wrong with the car, replace the component, i.e. doing a repair in their mind, and then send the car out thinking they fixed it, and the car comes back with the same symptom. Well, the reality is they never fixed it, and they never knew whether they fixed it or not because they didn't verify the repair. And this is also really important because multiple different things can cause the same symptom. So if I fix a car today and the customer comes back in 6 months and says, you know, my car's doing the same thing and you never fixed it. Well, if I didn't verify the repair, I wouldn't know if I ever fixed it or not. Maybe the customer's just been too busy for 6 months to bring it back. Maybe they've been out of town. Maybe they've been procrastinating. But if they verified the repair, now I know I fixed the last problem. This is a new problem. So I have two choices. Either the component I put in is defective, it's no longer working, or something to do with my repair, bad connection, something like that. Or the customer has another problem that they need to pay to repair. But if I never verified the repair, I don't know that. So no matter what repair we're doing, whether it's an internal engine repair, a cooling system repair, an electrical repair, we always verify the repair. Think about it. You wouldn't put a new light bulb in. Car has a headlight out. You wouldn't go, okay, I'll change the headlight. Okay, have a nice day, and never turn the headlights on to see if it works. Would you? That'd be silly. But yet people do that all the time with engine diagnosis or other kinds of more technical diagnosis. We wouldn't ever do that with a light bulb, but somehow we're going to do it with a couple $100 part. So you can see where that really creates an issue, and it creates an issue for both the shop and the customer because you don't know if you fixed it. In the customer's mind, if it has the same symptom, it's always the same thing. You know, kind of like a runny nose. Well, if I went to the doctor because I was sick and I had a runny nose, and then 2 weeks later, and then a week later, I still have a runny nose. Well, the doctor never cured me. Well, maybe you're cured, but now you have allergies. Or maybe you ate something spicy, or maybe, I mean, there's a lot of reasons why you can have a runny nose. Maybe you're allergic to the cat. Same symptom, different cause. So when we do a diagnostic and isolate a cause and we do a repair, we always want to make sure that that repair corrected the symptom that we're trying to diagnose. Because just testing a part and finding a bad part doesn't mean you're going to fix the car. So some of the tools we're going to use is a compression tester, measures the amount of compression generated in a cylinder. We also use a vacuum gauge, measures the amount of vacuum an engine can generate during various operating conditions.
Morning.
A pressure transducer measures engine vacuum or pressure and displays it on a lab scope. Cylinder leakage tester pumps air into a cylinder and measures the percentage of air leaking out of the cylinder to see how well it seals. A scan tool can communicate with the vehicle's computers through the diagnostic link, and I may be able to use like a relative power balance test or other tests. A stethoscope, either standard or electronic, to listen to unusual noises, see where the noise is coming from. So some of these are very high tech, some of them are fairly low tech. So the tools we're going to talk about is our compression tester, our vacuum gauge. We're going to talk about using a pressure transducer with a lab scope. I'm going to talk about a leak down tester, cylinder leakage tester, and we'll talk also briefly about a scan tool. So these are some, again, some of the tools we're going to see. I made videos on several of these, and there's lab sheets you'll fill out with the corresponding video. Here we see a standard stethoscope, an electronic stethoscope, and an example of indicators on the dash that might be letting the customer know we have a serious problem. Electronic stethoscopes are normally used for suspension work because we normally use electronic stethoscopes so we can put them in a place that I can drive the vehicle and the noise only happens when I drive the vehicle. So I need to put it different places so I can try to isolate where that sound is. Newer electronic stethoscopes actually attach to a lab scope where we actually get a scope pattern, and we can actually use that to triangulate in to where the noise is coming from instead of trusting our ear. So they become more and more high tech.
Never heard the name electronic stethoscope.
Electronic stethoscope. Yeah, electronic stethoscopes have been around now probably 30 years.
Wow.
One of the first ones on the automotive market was chassis ear. It was really designed for finding suspension noises. And it was pretty cumbersome to hook up because everything was hardwired. So you had to put the sensors and you had to hardwire everything back to your box. So it was pretty time consuming to put together and to try to find where the noise was. And now the newer one, you see this one's wireless. And then the newest ones are actually, they're going into a scope. General Motors actually contracted with a company called Pico. And they actually have a scope that all the dealerships are required to use. And you put different sensors on the car and go drive the car. And based on the waveform it creates, there's a database that says what's most likely making the noise.
Wow.
So pretty crazy, huh?
Very crazy. Never heard that.
Yeah, so someone took the time to do the research that said, if I put sensors in these places and the four patterns, the noise it makes looks like this, it has to be a loose seat. If it makes it like this, it's a loose shifter. If it makes it like this, it's a loose dash screw.
Right.
So someone had to put the sensors there and then deliberately make that problem, grab a capture, and then build software that the computer automatically recognizes it. That's just for GM. That's GM's factory tool. But pretty crazy.
Yeah. But as you said, the diagnostic is a two-kind test. If it is your car has a 50,000 mile or your car has a 200,000 mile. So both tests has a big meaning itself.
It does, because if the car's had 200,000 miles, what are the odds someone other than me has worked on the car?
Right, right.
So there's a lot more things, not only that can wear out, but there's a lot more things that someone else might have done that shouldn't have been done or were done incorrectly.
Oh, okay.
I could tell you the hardest thing to figure out or the hardest thing to fix is something someone else did wrong. Because people do things wrong in a way that a car will not normally break on its own. So it's much harder to find those things. That's why I hate working on a car after someone else has. So if I'm looking at sound diagnostics during cranking, engine noises can give me valuable insight into the condition. Is the noise coming from a starter that might be misaligned? The knock of a bearing, like a crankshaft bearing, uneven cranking sound from a low compression cylinder, very fast cranking from no compression, like a broken timing belt or broken timing chain. So these are some of the things we're looking at. Does it make a high kind of screeching sound? That's normally bearing damage from bearings that have gone dry from lack of lubrication, kind of like a high-pitched squeal when you crank it over. So again, we want to listen, and this is something that you only get by listening to other cars. Most of us, when we hop in a car, we really don't pay attention to what it sounds like when we start the car. We just put our key in the ignition and start the car because we're in a hurry to go somewhere. What we have to do as a technician is kind of listen to how different cars start. You know, I watch an old movie and I hear a car start, I know it's a Chrysler because older Chryslers sounded very different than Fords or Chevys did because they used a gear reduction starter instead of a direct drive starter. It made a very distinctive sound. You could hear them cranking across the parking lot. No, it was a Chrysler. So again, and that's something a lot of people just don't pay attention to. It's just, I'm just starting my car. I know the sound of a car that's cranking too fast because of a timing belt that's broken. Sounds kind of like a sewing machine. But I've seen new technicians really struggle with diagnosing that, where for me, I can hear it, it's broken, let's pop a cap and verify I'm right. Other students are going their traditional approach. I need to check spark, I need to check fuel, I'm checking the fuel, I'm checking all these things. Well, that's great. You're following the prescribed process that you should follow, but you're ignoring what your ears are telling you. What your ears tell you are not in that diagnostic process. What your eyes should tell you are normally not in that flow chart. For example, I think I mentioned this when we were doing charging systems. GM has a flow chart for a code for their computer for their charging system that if you go all the way down tells you to replace the computer. It never tells you to see if there's actually a belt on the alternator. And the car we had that came to us because they were told they needed a computer, the belt was missing off the alternator. That was the problem.
Hey.
So they missed it by that much. But they followed the flow chart.
Huh?
But what? They didn't use what's between their ears, their common sense. And they didn't use their eyes and ears that flow charts expect you to use, so they don't tell you those things. Rhythmic cranking sound, if the compression is similar across all cylinders, it should be sound very even, and uneven sound if the compression on the engine is not the same as each cylinder. Training to pick up sounds, disabling the engine of vehicles with good and bad compression can help you learn that. You know, some of us, because I don't hear so good, I have a hard time hearing a weak cylinder. I can definitely tell when a cylinder engine has no compression. So that is some of the stuff that we see.
Oatmeal.
Oatmeal? If
Sorry.
it sounds like oatmeal? Okay, so vacuum testing. Perform absolute vacuum measurements, determine the needed actions. So before we can really talk about vacuum, we need to talk about what makes vacuum. I'm going to take a couple minutes. I'll be right back, and then I'll explain what makes vacuum and then explain exactly what a vacuum test tells us and what it doesn't tell us. Okay, so let's talk about what makes vacuum. What makes vacuum in an engine? Okay, let me back up a minute. What is vacuum?
Vacuum is when you pull air instead of blowing air.
Well, I can pull air and not have vacuum.
Suction?
Okay, suction, but I could have suction and not have vacuum, right?
Negative pressure. Negative pressure.
Negative pressure. Okay, so pressure that is below atmospheric pressure, negative pressure. Okay, so vacuum is negative pressure or pressure below the pressure we have in the room around us.
Yeah.
So what makes vacuum in an engine?
Negative pressure.
When it pulls back after explosion,
When it pulls back up the explosion?
back from explode when the cylinder pulls down from after it explodes.
Right, so I explode, I've got the compression stroke and then the power stroke.
So when the valves close and the piston goes down, it creates a vacuum. I believe so.
Okay, so if I have a closed, so what I hear you saying is if I have a closed cylinder and I pull a piston down inside a closed cylinder, I will create a vacuum in that cylinder.
Yes.
Then that is 100% correct. However, when my piston is going down with my valves closed on my engine, that's my power stroke, and I have thermal expansion, so I'm really not creating a vacuum then. I'm what? Releasing pressure.
Mm-hmm.
So how does vacuum get into the intake manifold of the engine? Remember, if I've, because I know some of you guys took the brakes class, so we had what, a vacuum operated brake booster. Where does that vacuum come from? How is that vacuum made?
By pedal, we push the pedal again and again. A kind of mechanism make the vacuum.
No,
on that
doesn't make the vacuum. Our brake booster doesn't make vacuum. It uses vacuum. Vacuum has to come from someplace else.
Mechanically?
right? It comes mechanically from the engine. How does the engine mechanically make vacuum?
The crankshaft?
Well, the crankshaft just
No.
goes round and round.
What make a vacuum on
Right,
an
but
engine? What make a vacuum on an engine is when the explosion goes out. Something have to be replaced. When it pushes out, it have to be replaced by something. That's when it create vacuums, I believe. So it comes from the intake manifold because it's actually sucking air, oxygen, and fuel. So after the explosion, have to create vacuum.
Oh, so are you talking about the intake stroke where my intake valve's open and my piston's going down?
Well, yeah. When your piston is going down, it's create a vacuum or the pull from the manifold, intake manifold.
Okay.
right, so in the intake stroke, you have atmospheric pressure at the door, and the valve's open, and the piston goes down, so it pulls. The pressure wants to fill that negative pressure.
Right. So I can create vacuum in a cylinder that way, but how do I create vacuum in the intake manifold? Because you're absolutely right. Part of the equation is that piston going down, and I open that intake valve, so I create a low pressure area in the cylinder, and I use the air that's outside of the cylinder to fill that low pressure area. But what allows me to move that low pressure area out of the cylinder and into the intake manifold? Because if it was just the piston going down, diesel engines would have vacuum, and diesel engines don't have vacuum, even though they have a piston that goes down with an intake valve open. So what makes the vacuum?
What creates the vacuum?
What creates the vacuum in the intake manifold? You guys are 100% right on what creates vacuum in the cylinder, Mike, because obviously that piston is much bigger around than that small valve. So even though I'm opening up that small valve, that piston's going down, it's going to have lower pressure in the combustion chamber than it does outside the combustion chamber. You guys are 100% right on that.
But,
Now, my
but I
question
can't.
is, how do I move that lower pressure, not just in the combustion chamber, but into the intake manifold?
Mr. Brian, with the reaction of the 6 cylinders or 8 cylinders, it just it continues sucking air for the intake. It just
Yeah, but diesels do that too, and they don't make vacuum.
don't make vacuum.
Diesels don't make vacuum. Gasoline engines do make vacuum. So there's something on and they both have pistons, they both have valves, but there's something on a gasoline engine that allows us to make vacuum, and that's a throttle plate. The throttle plate, I mentioned this when we were talking about engines, the throttle plate is a restriction at the throttle body. I have a throttle plate, I have an intake manifold, and then I have my valve and a piston. As my piston goes down and the valve opens up, we want to pull air in. The throttle plate is restricting the flow of air. Because it's restricting the flow of air, there's going to be a difference in pressure on the atmospheric side of the throttle plate and the engine side of the throttle plate. That's what makes vacuum. That's why if I open my throttle all the way, I won't have any vacuum, because now pressure in the manifold and pressure outside the manifold are the same.
You're talking about the carburetor.
Or throttle body. It's really a throttle body, because carburetors have a throttle plate, but fuel injection also has a throttle body. We still use that throttle plate on gasoline engines. Diesel engines do not have a throttle. That's why they don't make vacuum.
Mm-hmm.
Okay, so the throttle is what actually creates the vacuum. Another way of thinking about vacuum is pumping losses. So when we talk about pumping losses with drive-by-wire, which we'll be getting into in a couple weeks, it takes energy to pull against that closed throttle plate. We're using energy to do it. We're using horsepower. That's one reason why diesels are more efficient, because they're not wasting that energy pulling against the throttle plate. But since that throttle plate in combination with the piston going down create that vacuum, that means vacuum is a mechanical function. So even though the book talks about ignition or ignition timing affecting vacuum? It doesn't. They're wrong. The only reason why it'll affect vacuum is you've increased the speed of the engine or decreased the speed of the engine. But the simple fact of burning the air fuel mixture does not have any effect on vacuum. And so you're going to see that in the book. They are wrong. And I can prove they're wrong. And I've done that before in hands-on demos. As a matter of fact, I prove it just by disconnecting an injector on the vacuum lab we do. Vacuum is a mechanical function. So vacuum is what's called a high-level test. A vacuum test will tell me if there's something wrong. It doesn't necessarily tell me everything's good, but it'll tell me if I have a problem. And it's a very easy test to do. And that's why people do it. So we used to use vacuum gauges a lot in the 50s, 60s. In the 1970s, we came out with ignition scopes, and they kind of replaced the vacuum gauge, even though a lot of scopes had a vacuum gauge on them. And these things were huge. I mean, these things were really, really big. They were, you know, as big as the screen behind me in some cases. And we would hook it up to an engine, and that would tell us a lot about the engine, the ignition scope. In the late 80s and early 90s, our ignition systems changed, made them much harder to diagnose. So that scope became much less used. And then OBD2 came along, and everyone said, oh, by OBD2, now I got a code tells me what cylinder is missing. I really don't need a scope, an ignition scope. But what we found is in the early 2000s is that the problems were no longer as much electrical or fuel related as they were mechanically related. And vacuum gauges have really come back. So now vacuum gauge is one of my first level tests because it'll tell me if I have a mechanical problem pretty quickly and tell me if I need to do other testing. It's just a good thing to do. It's real quick and easy is one reason why we do it. So it's funny how things come full circle for something that used to be a very used tool to not being used really at all, to completely disappearing, to then coming back and being right now a very widely used tool because the information gives us. Because what we had is in older cars, 80s, the ignition or fuel systems would break before the engine did. Now we have cars engines are going, you know, the electronics will go 300,000-400,000 miles, but the engines might break at 125, 200, 250,000 miles. So we're seeing a lot of engine mechanical failures now, causing rough running or misfires or things like that, where we really didn't see that so much 20 years ago. It was normally ignition or fuel because those are the things that wore out first. So the vacuum gauge is used to determine the engine's general condition, mechanical condition. It shows the difference between the outside atmospheric pressure and the amount of vacuum in the engine measured in inches of mercury. Installed in a vacuum port on the intake manifold. A typical vacuum reading on a properly running engine at idle, warmed up at idle, AC off, is going to be between 17 and 21 inches of mercury. And that is just a good general range. Higher is always better. So if I'm at 20 or 21 inches, I'm a lot happier than if I'm at 17. If I'm working on an older car, 17 is actually too low. If I'm working on a car made the last 15 to 20 years with the drive-by-wire technology that we'll talk about, 17 is a normal number. We used to say 18 to 21 used to be the normal number. Low reading could relate to a problem with valve timing, excessive piston, piston ring gap or wear, cylinder wall wear, anything to do, valves not opening, valves not closing. Think about it. All our engine is an air pump. It pulls air in and it pushes air out. Just like the air compressor we have that generates air for our air tools, it's an air pump. All we're doing here is I'm using the restriction of the throttle plate to measure the efficiency of the air pump by measuring how much less than atmospheric pressure it's able to generate. Sharp oscillation back and forth in the needle or a dip in the gauge reading could relate to a problem such as a burnt or sticking intake valve. So if I have an intake valve that's sticking or burnt, my needle will move very rapidly like this. An exhaust valve won't cause that. Only an intake valve will. So remember what I said, I can figure out what's not wrong here, but it doesn't tell me everything that could be wrong. Low reading once the engine reaches higher engine speed could indicate a restricted exhaust or a faulty variable valve timing system. So I did put this chart in here. This is not in the book. So 17 to 21 inches, good reading. Drive-by-wire and Atkinson cycle engines can get as low as 15 or 16 inches and still be normal. Keep in mind, vacuum at idle is created by the restriction of the throttle. So if my idle air control motor is stuck open, I'm going to have less vacuum. If my car is running bad because of bad ignition or bad injector, the throttle will be opened further if it's drive-by-wire, or the idle air control motor will be opened further, allowing more air into the engine to keep it running. That's going to be less vacuum because there's less restriction. On the other hand, if I have a car with an idle air control motor that's stuck completely closed, or someone adjusted the throttle completely closed, I'd have much higher vacuum. We see that especially on a cranking test. And actually on the video I did, you get to see that. Needle oscillates back and forth. We talked about that. Low and steady reading, possible late valve timing, idle air control motor is open too far, idle speed is too low. Snap acceleration, the needle drops to 0 and then only reads 20 to 23 inches of vacuum upon return to idle. Should be much higher, around 27, possible worn rings, plugged exhaust, vacuum leak, things like that. Good reading in idle, as the engine speeds up to 2,500 RPM, the needle slowly drops and may continue to drop. Restricted exhaust. So here's a real inexpensive tool that I can hook up to an engine and do a series of tests and get a great deal of information. So you see why, as hard as it is to get to things like even spark plugs on some of these new cars, where technicians would be going back to this vacuum gauge. I used a vacuum gauge the last 8 years I was in industry far more than I did the first 30 years I was in industry combined. So this is a tool that we really use today. So there's a couple of different ways I can do vacuum testing. One is with a mechanical gauge, which I demonstrate in the video I did, which is on Canvas. The other is I could use a lab scope and do a vacuum trace. Now, I have the equipment to do a lab scope trace. I have never found it terribly beneficial. I've never gotten extremely good at it. I understand the theory behind it. I've just never found it terribly practical from a diagnostic standpoint. So the book spends a lot of time talking about it. I got some slides. I'm going to talk about it briefly, but in full disclosure, this is not a test I did in the shop. It's been around forever. It's been around. We've had vacuum transducers going back at least 25 years now that we've used because we used them on scopes. I've just never been that sold on it. Never used it to help me fix a car. It is there. There are some people that really swear by it and really like it. I use a scope for a lot of things. This is not something that I ever really got in the habit of using a scope for. I stuck with the mechanical vacuum gauge. So the mechanical vacuum gauge needs to be plugged into a source of manifold vacuum. So we connect the vacuum gauge. You might see the vacuum T. Other sources might be, one of my favorites is where the purge valve goes in, because the purge valve vents right by the throttle body. What I don't really want to do is go into a vacuum port that's only connected to one cylinder. I want it connected to all the cylinders in the plenum or up by the throttle body.
So you have to be connected by the intake manifold instead of spark plug.
The question I have, that vacuum and scope. So what is the transducer on the vacuum showing the scope as an indicator with respect to time?
I will show you how to do that. You're about a couple slides ahead of me.
Okay.
Great question. And I'm going to answer that for you.
Sure.
So make sure the engine is at operating temperature between these before we do these tests, or the test will not be accurate. Start the engine and take a reading at idle and record the reading. Then accelerate the engine quickly by opening and closing the throttle. Record the highest vacuum attained. So I want to do two things. I want to see when I first open the throttle, vacuum should go to 0, because what I've done is I've just taken the throttle plate and done this with it. So now the pressure here and the pressure here should be equal. And since I opened it so fast, the engine hasn't had time yet to speed up. So all I did is just dump a whole bunch of air in, and my pressure should have equalized. Then when I rev the engine up, the engine revs up, it's going fast. Now I quickly close the throttle. So now the engine's going really fast, and I just put a big restriction in. So vacuum's going to go above what it was at idle. If I hold steady at 2,500 RPM, my vacuum should be higher than it is at idle by 1 or 2 inches of mercury and should not drop. If it doesn't get higher, or if it steadily drops as I hold it there for a minute or two, that's a sign I have a plugged exhaust. So which of the following vacuum ranges is a known good result for an idle vacuum test?
4.
Absolutely, 4.
8 and 21.
So one of the vacuum tests that I just realized there's not a PowerPoint slide on it. I do it in the video, is a cranking vacuum test. If I do a cranking vacuum test, that's where the engine's not going to start, but I'm just cranking the engine over. I should see about 3 to 5 inches of mercury of cranking vacuum. So that's a way of telling you what, is my timing belt broken? Is my exhaust completely plugged, which I've seen? Is everything going around, and is the engine able to move air? So it's a great, just quick mechanical test. If I have a car that doesn't start, before I do a compression test, throw a vacuum gauge on it. It's a fraction of the time. Crank it over. Do I have cranking vacuum? If I don't have cranking vacuum, then that warrants a compression test, or my throttle's stuck wide open. But if I have good cranking vacuum, low compression is not why the car is not starting. I just saved myself an hour's worth of work. So if I'm going to use a transducer, I would hook the transducer to the same place where I would hook a vacuum gauge. And this is what's in the hand right here, is a transducer. And then that transducer is hooked with a 3-wire connector to the scope. And this next thing you want to do is I need to synchronize, which is what Saeed asked me. How do I know which is number 1 cylinder, or which is any cylinder? So I need to use a second channel on the scope. So what I'm going to do in this case is I'm going to use this spark plug lead, and I'm going to go around the spark plug to number 1 cylinder. So now I know when number 1 cylinder spark plug is fired, and I know we fire number 1 spark plug very similar to top dead center on the compression stroke for number 1 cylinder. So then you saw that chart that I showed you in the last PowerPoint. Hey, when number 1 cylinder is on compression, what cylinder number 2, what cylinder number 3, what cylinder number 4 doing? And then I can figure out what comes next and what everyone's doing. So here's what this would look like. So I start the engine, let it idle, adjust the scope so it captures the vacuum pulses in all the 4 cylinders, in this case, and observe the trace. So what I'm looking at here, this is when I fire number 1 cylinder right here. This is when I have a cylinder on an intake stroke pulling the most vacuum. Okay. So this is an intake stroke, an intake stroke, an intake stroke, an intake stroke. This is when number 1 was at top dead center compression. So what I would need to do is I would need to use that chart I showed you and go, when number 1's at TDC compression, what cylinder's on intake right after that? Because that's going to be this cylinder. And then the next cylinder, the next cylinder, the next cylinder. So this right here would be number 1 cylinder, right?
So Brian, what is,
No, this would be number 1. Could it be intake, compression? So this would be number 1 right here. Right? We have 4 strokes. Because if this is compression, then I need to go power, exhaust, intake. That's number one. What's my firing order? 1, 3, 4, 2. Well, if it's 1, 3, 4, 2, and this is number one, that would have to be number 3. That would have to be number 4. That would be cylinder number 2. So that's why we do that, Saeed.
Brian,
Yeah.
what is the red line?
The red line is my ignition primary. So that is my ignition system. That is when it is, the spike right here is when it actually fires the spark plug. Actually, it's ignition secondary on this one, but they mimic each other. But that's when it's actually firing the spark plug.
So my question is again, sir,
Yeah.
that the scope reads only electrical signal.
Right.
So what is the transducer name to get the vacuum pulses for all cylinder?
Okay. So what the transducer does is it converts a pressure signal into an electrical signal.
What's the name of the transducer? That's I'm asking.
In this case, it'd be a vacuum transducer
Vacuum transducer.
or a vacuum pressure transducer.
Okay.
So it'd be a vacuum transducer, normally 0 to 30 inches of mercury vacuum transducer. And that would allow me to see those pulses with a great amount of detail.
Oh, so mercury measurement.
What's that?
That's a mercury measurement of the, that's
Yeah.
showing the pressure of the vacuum, which is vacuum is minus, negative.
Right. So down negative, up positive. So it is a measure, and you got to be careful there because how does the transducer read? How does the scope set in?
Right.
So normally they read pressure. So they're really not reading vacuum, they're reading less pressure or negative pressure. That's why higher vacuum is lower, because I'm really not reading vacuum. My scale wouldn't say inches of mercury. It's going to be all in PSI.
Okay, I got it. Thank you.
So really what I'm looking for here is I'm really looking, are all these the same at the bottom? And are they all basically the same at the top? So if I took a line across, would that all be about the same place? If I took a line across the bottom, would they all be at the same place? What we're really looking for here is something that's different. So the book talks about go find a known good pattern to compare it to. Clue, there isn't one, okay? What you're really doing is comparing it to itself. Because if I have one bad cylinder, which is what this test is designed to help me find, it's designed to let me know which of my one cylinders has the bad valve. For example, maybe I have a bouncing needle, means I have an intake valve that's not sealing. I could do this test and it would help me locate which of those cylinders it is. The point is, I have other tools to help me find that are much more accurate, much more efficient. That's why I don't do this. So again, here I'm zoomed out, but what I'm really looking at, I'm looking at my peaks. Are they pretty consistent? I'm looking at my valleys. Are they pretty consistent? What you don't want to do is get lost in what this looks like on each cylinder, because you see it changes, because this cylinder here is the same as this cylinder here, which is the same as this cylinder here. So you can see it can change a little bit from cycle to cycle. If I had one that looked very different every time I saw it, that would be a concern. So again, this is all about, does everybody look the same? Does everybody always look the same? That's what we're looking at for. If someone always looks different, then we assume that there's a problem with them. So we do a lot of this in automotive because there isn't a good spec. There isn't a good picture. There isn't a, this is what it should look like. What we're doing is we're using all the cylinders on the car, in this case, 4 of them, and we're using what should be 3 good cylinders to find the one bad cylinder. And we're doing that because the one bad cylinder would look different than the 3 good cylinders. Or if it's an 8-cylinder, the one bad cylinder would look different than the 7 good.
Transmisiones en vivo desde el lugar de los hechos.
What, Gabriel?
I'm sorry, no, something came on.
So we can see here, we're zoomed in a little bit. Here's where I'm firing the spark plug. We can see my tops are all pretty equal. We can see the bottoms are also pretty equal. Now I do notice that this bottom looks different than these bottoms, but not that much. It looks similar to that one. If I had a car that's running bad, I might zoom out and see, does this always look different than these? Or is it just this one set of 2 revolutions, 720 crankshaft degrees that I zoomed in on, that one just happens to look different this time? So that's the advantage of a scope, is being able to zoom in and zoom out and see, is this anomaly happen all the time? Or is it just the pattern's not that good and it dances all over the place? So here they're talking about 12 to 1500 RPM and then go up to 2500 RPM. And again, really what they're looking for is equal. The PowerPoint says, you know, compared to the trace to known good readings, there are no known good readings. You're comparing the trace to itself. The whole key thing is I've got all 4 cylinders. All 4 cylinders should be looking pretty equal. Here I can see number 1 cylinder does look different than the other cylinders. I would question why. It has higher here. But again, the first question you need to ask is, how's the car run? If the car runs good, who cares? And that's the problem with some of these tests. When you're trying to play with this, people tend to find problems where there isn't one because the pattern doesn't look perfect. Well, if the car runs good and it's not setting any codes, it's normal. It's just within how that tests. And that's why if you're going to use a test such as this test, you really need to look at a lot of cars that don't have a problem. The mistake we make in the auto industry is we have tools like this, and we buy these tools to help us fix a car, and the tool collects dust. And we only pull the tool out when we actually have a broken car in front of us, and then think we're going to make smart decisions. And it's not just entry-level techs that do this, it's advanced level techs do this. I'll be teaching a class tonight where people are going to bring in a lab scope that they've probably had in the shop for 20 years, and they still don't know how to use it. But yet they try to use it every time they have a car that they can't figure out. But they're not proficient at it. They don't know what good looks like. They really don't know what they're looking at because they haven't invested the time to learn those things.
Sure.
Anything you want to learn, you need to know what good looks like before you can figure out what bad is. If all you ever do is look at things that are broken and never see what things are supposed to look like, you're going to make a lot of poor decisions. Speaking of someone who's made a lot of poor decisions. Because for some reason, we have the idea that we can't use the tool until we have a broken car. Yeah, Gabriel, I'm sorry.
When let's say you see something different on one of these pistons,
Right.
can that okay, on some of them you say, okay, something wrong with a valve or something wrong with the exhaust.
Right.
But what if the spark plug is not firing? Would that show on this vacuum too, or?
It shouldn't. It shouldn't, because vacuum is created by the mechanical function of the piston going down against the closed throttle plate. That has nothing to do with whether I had an explosion in the combustion chamber or not. And I've actually disconnected spark plugs and seen no change when I've done this pattern playing with it. Because I've done that in labs. To get people really through the concept that this is a mechanical test. This has nothing to do with my spark and fuel. I'm only testing, is my air pump any good?
Okay, I see.
And if I see a problem with a cylinder, that just tells me I need to go run another test. But now I know which cylinder I need to run the test on instead of running tests on all the cylinders.
So in another way, you go, let's say, cylinder number 3, you just go and connect it. You connect that pressure.
No, if I thought I had a problem in cylinder number 3 on this test, which is a vacuum test, the next thing I'd probably do is a compression test.
Yes, exactly.
Okay. So, again, that's why this is called a high-level test. It could tell me very quickly if I don't have a problem here, but it won't necessarily tell me specifically what the problem here is, just that I have one. Well, so it justifies tests that take a while. So in auto, we do a lot of what are called high-level tests, very quick tests to where I can exclude things that can't be the problem. And that allows me to look and see if this can't be the problem, what's left has to be my problem. And so even though a lot of high-level tests, they don't tell us what is wrong, they really tell us what's not wrong when they pass the test. So another way I can find what cylinder is misfiring is doing a power balance test. So this is used to identify cylinders that are not operating properly when a vacuum test or cranking sound test indicates a mechanical issue. Well, what I can tell you is, great question, Constantine. It depends on what kind of compression test I'm doing. A cranking compression test tests for different things than a running compression test. And I'm going to break both of them down as we move through this. The reality is I'm going to do a power balance test or a cylinder balance test before I do a vacuum test. That's one reason why I don't use the vacuum test with a waveform on a scope to try to find the cylinder. Because I'm going to use a power balance test for that to find the weak cylinder normally. And then there's different levels of power balance tests we can do. And sometimes they're inconclusive. I just uploaded a video. I got to finish building the page where I did a power balance test. And I tell you which cylinder I think it is, but it was really inconclusive. We needed to do another test. So I did another test using different tools and a more high-tech tool to do a power balance test. It turned out I was right on which cylinder I thought was bad. But I took a lot of voltage hits doing it at 30,000 volts a shot. So I was getting hurt after it by the end of it. Yeah, Gary.
Mr. Brian, okay, like when people bring their car in for overheating and then they say we got to do a compression test on it, is this what we're talking about?
Yeah, but I don't know why we do a compression test for overheating. There's really, that's not how I'd address an overheating complaint. It's an inefficient way to get to an answer. Normally, if I have a car that's overheating, I would do a cylinder block check, which is a chemical check, where I'm looking for carbon monoxide and hydrocarbons in the cooling system. Because if I've blown a head gasket or cracked a cylinder head, I'm going to see combustion gases coming into the cooling system. If the car is running so bad, I mean, if the car won't run at all because I've blown the head gasket, if I fill up the radiator, take the radiator cap off and crank the car over, I'll get a geyser that'll hit the ceiling on a good day. Why would I charge the customer an hour or two to do a compression test when I can fill it up with water, take the cap off, crank the engine over? And my favorite thing to do back in the days of service stations was have the new island guy come over and watch the radiator to tell me if the water moved when I did the test.
Okay.
Right? I mean, you always pick on the new guy. We just do. And
That's a new one to me.
Man, gee.
so that's right. So, you know, and of course, everyone else who works there has probably already been the NG guy at least, and he's already gotten to do it. So no one's saying anything to him. Kind of sounds like the military almost, don't it?
NG.
Yes, it does.
So, you know, there's a lot of tests here. The question is, what test is going to give me the most information with the least amount of work? What test is appropriate to what I'm trying to find out? So I could find out if I had a blown head gasket possibly with a compression test. However, I might pass a compression test with a blown head gasket.
Also, well, what you're saying, can like we do that test ourselves? Is there something we can buy to do that test?
Absolutely. Absolutely. These are all tools that you can buy. And a lot of them that I'm showing you, the lower level tools, are not that expensive.
Because you say you're
upper
checking
level
for something
tools-
in the antifreeze, correct?
Yeah. Yeah, and I when we get into cooling systems in another week and a half or so, I'll show it to you.
Okay.
And so again, all these different tools, some of them are, $10, some of them are $30, some of them are, $40 or $50. Some are several $1,000s. The point is, I need to know what a $30 tool will tell me, and I need to know what it won't tell me. In other words, a $30 tool will probably find the problem 80, 90% of the time. At home, that's probably all I need. If I'm working and all I do is diagnose cars that run bad, now I probably need to figure out how to fix that last 10%. I'm probably going to need to buy that expensive tooling in order to be able to fix those cars.
Okay.
Right? But if I don't show you the expensive tools that you're never going to buy to understand what they can show you compared to the other tool, you'd be under the false assumption that, hey, it passed this test, so it's good. Not, it passed this test, which means I proved this and this, and I haven't found a problem, but I still could have a problem, and these are the problems I didn't test for. That's where the value comes in.
Okay. What is this test? I'm probably getting off the subject. What is this test when it's like smoke or fumes or something they'll put through the engine some kind of way?
Right. So that is a smoke test on the intake system that we use to find vacuum leaks.
That's what I'm talking about.
We routinely do that on a car that has a P0171 174 code, a fuel trim code. Because the most common cause of those codes when they set at idle is a vacuum leak. So again, I can test the injector flow rate. I can test fuel pressure. I can do all these things. Or I can go test the thing that's easiest, that's 80% of the time is the problem. I'm going to do that. Okay? It doesn't mean that is the problem. It doesn't mean I'm going to find the problem. But since it's probably the problem 80% plus of the time, it makes sense to do the test first. That's the smoke test. And thanks for bringing that up, because I need to do a video on that. Because I have my smoke machine here. And that'd be a good video to do. So I'll have to do that on my Toyota or something. As we're moving into that. So that's good, because I hadn't thought about doing a video on that, and I should. So, but that's what they're doing there, is they're looking for vacuum leaks. And that's one of several ways we have of finding vacuum leaks. And the smoke machine is not 100%. I can have a vacuum leak, but it won't smoke, because smoke is very low pressure trying to get out, where vacuum is very powerful pulling in. So if I have a seal, maybe the seal has enough integrity to hold that less, half a PSI in, but it can't keep 20 inches of mercury from pulling that seal and letting air come in. So again, with any test, we need to understand what it tells us and what it doesn't tell us. The other thing is, in the case, and we are off the hair, but we're on engine testing, and so it's real valid. If I'm smoke testing an engine, I want to smoke test the engine under the same conditions that the code set. So if the code set in the morning when it's 60 degrees and you brought the car into me and you want to wait, we're going to have a talk about how you're going to leave the car overnight with me. Because just because it passes now, all that tells me is I have to test it when it's cold. Because the leak isn't, because think about it, my plastic expands, my metal expands, everything's gonna maybe expand together when it's hot. When it cools down, it pulls apart, now it leaks.
Okay.
So when we get into OBD2 and get into computers, I'm gonna talk about freeze frame data a lot. That's where we get the information on exactly what the car was doing when the code set. That way I know when and how to test it. So back to our power balance, a general indication of each cylinder overall health. So what we're doing here is, I'm not saying are they all good or are they all bad. but do they all contribute the same amount? Are they all pushing an equal amount when they push the piston down and try to make my engine go? Or is one of the guys just kind of along for the ride eating a chicken sandwich? So we want to see, is everybody working? So this is our power balance test, also sometimes called a relative compression test, because we're kind of looking to see, is everyone doing the same thing? Test contribution to each cylinder, the engine's output by disabling one cylinder at a time and measuring the RPM drop. Cylinders that are correctly operating and improperly working are going to be identified. The greater the difference in RPM drop, the greater the difference between the cylinder's ability to produce and share the engine's power. Idle speed electronically controlled through the PCM, we want to disable. And a manual power balance sheet use the PCM's built-in power balance feature. So some cars have a power balance feature where I can go in and turn off cylinders one at a time and see if they're equal. Just because it passes a power balance test doesn't mean they're all working evenly, though. I'm only getting part of the picture here. Visually inspect the engine to determine the best method to disable the cylinders. If necessary, disable the idle control system, normally just by unplugging it. Start the engine, allow it to idle, record the engine RPM. And then as you disconnect either injectors or coils, one at a time, you want to see how many RPM it drops. So if I disconnect my first cylinder and it drops 50 RPM and all the other ones drop 50 RPM, I get cylinder number 7 and it doesn't change when I disconnect it. Guess what? That's the cylinder that's not producing any power. So this test is great at finding the cylinder that's not doing anything. It's not real good for finding cylinders that are intermittently not doing something, or, you know, kind of sometimes I'm good, sometimes I'm bad. But this is a good quick test. This test really requires no tools, even though we're using a scope here to measure. In this case, we're using a scan tool to disable them. Or if I'm manually disabling them, I'm using a tachometer. Most of us can hear, if I disable something, we hear the engine run differently. All I'm listening for is when I disconnect it, did the engine run the same? If it runs the same, whether I disconnect it or not, that means that cylinder didn't do anything. So as I disconnect cylinders, I should hear a plug it back in, boom, I'm happy again. Pull out, plug it in, boom, I'm happy again. If I pull it out and I don't hear any change in how the engine runs, guess what? That cylinder is not doing anything. It's not contributing any power. So that's a very quick, no tools test. On some cars, it's more accurate than others because some cars are running worse than others. Yeah, Gabriel.
Yeah, once you do that, or we do that, we can check the spark plug or the wire, or we can check the compression of that cylinder. Is that
right? So once we isolate the cylinder, then I want to check for spark, I want to check for fuel, and I want to check for compression. And I have a video I did where I do this on the same Jeep. I did my relative power balance test that I got shocked the heck out of. I put a high-tech tool on, verified the cylinder, and walked through the whole process. I'm probably going to save that video for when we get more into engine management, because it really talks about how I test spark and how I test fuel. And I really want to cover spark and fuel before I have you guys watch the video. And not that I couldn't put it up sooner, and I may, if people want me to, I will. But it really walks me through how I take a cylinder that's not producing power and through process of elimination, figure out exactly what it has to be. And that's really what we're doing. I only need 3 things for a cylinder to run. I need spark, I need fuel, I need compression, and I need to mix those things at the proper time. So if I only have one cylinder that's not running, it can't be timing, because I'm not going to have one piston that's out of time from the rest of the piston. I'm not going to have one set of cam lobes that's out of time from the other cylinders. I'm not going to have ignition for one cylinder that's different than ignition on all the other cylinders as far as timing goes. So therefore, if I only have one cylinder that's misfiring, it can't be timing. So now I'm down to just spark, fuel, compression. What I do is I check for spark and I check for fuel. If they're good, it has to be a compression problem. It just does. If I've got good spark and I've got good fuel, and it doesn't burn, there has to be a problem with the cylinder. Now the trick is figuring out what that problem is. It's much easier to test spark and fuel than it is to test the engine. So it makes sense, right? We test the easy stuff. Plus, we have a lot more spark plugs, a lot more ignition coils, a lot more fuel injectors go bad than we have engines go bad. So it makes sense I do the easy tests first that are what most likely is wrong, and then once I prove they're good, now I can get into the hard stuff of figuring out exactly what's going on inside the engine. Everyone follow the logic there? So I may go ahead and post that up for this chapter because I did do the video on it. It's on the, I think I published it. I think it's on the public side of my YouTube channel. If you guys haven't subscribed to the channel yet, if you do, you'll see anytime I post a public video, because I post videos I don't use in this class also that have different things on them.
Do you have a link for your video for your channel?
Yeah, let me see. I should be able to do that.
Well, video always help.
Yeah. The video always helps. Let's get here to dashboard. I'll just throw up a link for a video. Probably the easiest thing to do. Like I just did one on top end engine cleaning, installing a new O2 sensor and testing it, different converter testing. Let's see if I can find misfire diagnostic. There we go. I just sent the link to one of my videos on YouTube. That way you can find that way it'll take you right to the video so you can subscribe to the channel, and that way you'll just get all the posting and all that. But it all comes down to what? I mean, there's a lot of tests out there. Which tests are going to give me the most information? So it does make a mention, do not leave the cylinder disabled for more than a few seconds. Well, here's the deal. If I'm disabling ignition, I don't want to leave it disabled for more than a few seconds. We're talking 10 seconds. If I disable fuel, if I disable a fuel injector, I can leave it disabled as long as I want. It's not going to hurt anything. That's why if we have a choice, the preference is to disable injectors. You'll see on the one video I did, I didn't want to break connectors, so I disconnected spark plug wires and I paid for it. Reactivate the cylinder, allow the engine to run for at least 10 seconds to restabilize, and then disconnect the next cylinder or deactivate the next cylinder. And we can see in the picture here that cylinder 4 had a lot higher change than the other one. So as we go through, I'm looking, do they all have the same amount of change, same amount of RPM change? So let's talk about cranking and running compression tests. So we use the same tool for both of these. We're using a compression tester, whether I'm doing a cranking compression test or a running compression test. And this uses a high pressure hose that's hand threaded in the spark plug hole and then connected to a compression gauge. On the end of the hose, it uses a Schrader valve, very similar to the Schrader valve we'd see in a tire. And it does that so that every time I come up on compression, it can capture that pressure in the gauge side. So it'll build up to my maximum pressure. So the compression gauge reads the amount of pressure that the piston produces in the cylinder with the valves closed. Cranking compression indicates how well each combustion chamber is sealed. The book says the engine's ability to breathe, volumetric efficiency. That is not correct. And instead of just deleting this, since I know this is in the book, it's just flat out wrong. The cranking compression test only tests if a cylinder is able to seal. It doesn't test if it's able to breathe. So I can have an exhaust valve that never opens and still have good cranking compression. But that cylinder can't breathe. It has no place to put anything. It can still pull stuff in. It can create a vacuum, pull stuff in. It can still compress it. What can't it do? It can't get rid of it on the exhaust stroke. It's just like having two compression strokes that I come back in, and what? I've got that same action of creating what? Vacuum inside the cylinder to fill it up again. I'll have good cranking compression with an exhaust valve that never opens. That's why cranking compression does not test the engine's ability to breathe. The book's 100% wrong.
But if you put a vacuum on it, you can get the other results on the other
On
valve.
a vacuum, on an idle vacuum test, I would have low vacuum, but it would be steady. The needle would most likely not be moving very much.
All right.
But I would have low vacuum. I would be below that 18 to 21 range. Because I'd only have what? 3 cylinders pulling, not 4. And I'm displacing because I've already filled that cylinder once. So when I come up to top dead center, I've got pressure. I'd open that intake valve. I'd get a little bit of bump of the needle. I might get a lot, but then it's pulling it back down and it's pulling it back in. So my regular vacuum would be low and my needle would have some movement.
Mr. Brian, if exhaust valve is open more than the gauge is open bigger than what requires, would that take effect on the engine? The exhaust valve.
It would. So if it's open longer or if it's not sealing, I'm going to lose compression. So like a burn exhaust valve would cause me to lose compression in the cylinder. So a burn exhaust valve, because it's a sealing issue, I would see with a cranking compression test. If it's not opening properly, that's a breathing issue. I will not see that with a cranking compression test. A
No,
running compression test, I will.
no,
So
but
running compression test checks my ability to breathe. A cranking compression test tests my ability to seal.
yeah, no, I'm sealing good, but just open it more than normal when it opens.
Right. So that would affect my running compression.
All right, okay.
So remove any spark plug wires, coils, connect directly to spark plugs, disable the ignition primary or secondary system, ground the wires. They talk about disabling the fuel pump fuse. When I did my video on this, I cheated. I showed you how to use a remote starter on the starter so I could just keep the key off so I don't need to worry about finding the fuel pump fuse. You remove all the spark plugs. So compression tests are traditionally, in how we teach them in the class and how I'll demo it, if I'm going to do a compression test on an entire engine, I'm going to remove all the spark plugs. If I'm going to do a compression test because I have one bad cylinder, I'm only going to remove the one spark plug. Because I'm not looking for evenness. When I do a compression test, the reason why I remove all the spark plugs is, for one, I'm going to test all the cylinders. The other is, by removing all the spark plugs, I increase my cranking speed, which means that the faster the car cranks over, the more compression I can generate. If I'm diagnosing a cylinder that has a misfire code and I think it's a compression problem, I'm just going to test that one cylinder, because the problem I'm looking for is going to be so big. If it's a compression problem, I'll see it. I'm not worried about comparing it to everybody else. I'm worried about, is this really bad? So for example, if I run a compression test and I'm supposed to have 180 pounds compression and I'm misfiring on a cylinder and I just test one cylinder and it's 90, do I really need to test the other cylinders? 90 is bad. It's half of what it should have. At 90, actually anything under 100, it won't burn fuel. I've found my problem. And furthermore, am I going to take apart the engine and only fix one cylinder? Or am I going to take apart the engine if it's a burned valve and have all the valve job done?
Yep.
Right? So
Yep.
why should I waste my time checking everyone else? I found the problem. Pull it apart, let the machine shop tell me what I need.
Now, if you remove all the spark plug, what happens? It will crank or no crank?
It'll crank, it won't start, but you crank it over with all the spark plugs out. So here it talks about removing all the spark plugs, connect the compression tester to one of the spark plug holes with the gauge attached, hold the throttle down all the way. We want to open the throttle. you're going to get a different amount of compression with the throttle open or the throttle closed, because with the throttle closed, we create cranking vacuum. Under vacuum things way less. I have less density. So when I go on the compression stroke, I'm going to have less compression pressure. So we always want to hold open the throttle when we do a cranking compression test. We want to go through at least 5 compression cycles. However many cycles you use, whether it's 5 or 8 or whatever, you want to use the same number of cycles on every cylinder, because we're going to compare our cylinders to each other. So it would be unfair to have one get 5, another one get 8, maybe one gets 10, one gets 3. And then, gee, I'm surprised my readings are different. So the whole thing here is consistency. Record the first and last needle readings. So the first needle reading is what's called the first puff. The first puff goes up. That's what tests the sealing of my rings. And then my high total reading tells me the sealing of the cylinder. Repeat this procedure for the other cylinders and compare it against manufacturer specifications. Manufacturer specifications generally want all their cylinders to be within 10 to 15% of each other. They want them even. Think about it. If they're not even, the car's not going to idle smooth. Now, if I have a cylinder that's low, traditionally we would do a wet test. And the wet test, we would pump some oil in and it would go around the rings. This has not been done in the industry for 30 to 40 years because it's not accurate. The wet test came A, when we didn't have the tools we have now, and B, when straight engines were in line. So all the pistons sat what? Like this, flat. So if I squirt some oil on it, and it wasn't a dish piston, it was a domed piston. If I squirted oil, the oil would leak over, get down to the ring, go around the rings, and if compression went up, that meant my rings were losing compression. Now, how do we build a lot of engines? They're like this, aren't they? As well as my pistons are no longer flat on top. So if I squirt oil in, I got some oil on the bottom. Is there oil on the top? No. So now I'm doing this wet test and going, oh, it didn't change, so it must need a valve job. I do a valve job and I have the same problem. Why? Because we never tested the rings on the top of the cylinder. That's why we don't do that. Okay, so this is a great 1940s, 1950s, even 1960s test. In the 1960s, this really cool tool started coming into the shop a lot, called an air compressor. And we started getting things like hoists so we could put cars up in the air. Crazy time in technology in the 1960s. So once we got air compressors, by the 1980s, we developed what was called a leak down tester or cylinder leakage tester, where we put a calibrated amount of air in and measure how much air comes out. And on top of that, I can see where the air goes. So I can tell you if the intake valve's leaking, the exhaust valve's leaking, or if the rings are leaking, or if the head gasket's leaking just by doing the test. So we don't wet test cylinders anymore in the industry. We just don't. But yet the books are like 40 years behind the time and think that everyone should know how to do it. So I talk about it. It's just not something we do. I'd rather talk about why we don't do it so we understand why we don't do it. Here's the other issue we have. I'm testing cylinder sealing with a piston that's this big around. My valves are this big around, and I might have a hole this big around in the valve. Well, if I have a piston coming up pretty quickly, the piston's displacing a lot more surface area than that little hole that I have. I could still have compression in range, even though I have a valve that's not seating because of a piece of carbon on it or slightly burned. So even though it tests cylinder sealing, it's not 100%. I could still have a really small product. Think about it. I'm pushing this big area really fast. I can't let it all out this small area. Therefore, there's going to be pressure generated. It may be slightly less than my other cylinders. Is it going to be 10% less, 15% less, 20% less? Who knows? I've seen plenty of cases where it's really not measurably less. So it's important when we do a compression test to understand what the different tests tell us, and more importantly, what they don't tell us and what I might be missing. So I'm going to end today with a question. A cranking compression test evaluates which of the following?
Cylinder sealing.
Cylinder sealing. So when we come in next time, we're going to get in and we're going to talk about running compression test tomorrow, leak down test, and our other tests that we use on testing the engine. And we'll wrap this up tomorrow. And I'll probably do an animation and we'll look at some video stuff tomorrow. So this is all about testing. And a lot of tests are, why do I choose a certain test? Why do I use this test instead of another one? So on that note, everybody be safe and have a great day.
Animations help.
For the wet test, you said the spark plug generally got wet. It is an old car. Is that right?
What about the spark plug being wet?
Wet by the oil.
Right, but is it wet from the oil because there's no spark? Is it wet from the oil because I'm using too much oil? Is it wet from the oil because I have too much fuel and it fouled it and washed the cylinders? A lot of
multiple reasons. Multiple reasons. Yeah.
It can be multiple reasons. So the question is it dried? Is it dry caked oil on it? Meaning that it's oil that's gotten in the cylinder and burned and attached itself to the spark plug? That's an oil consumption issue. But if it's all wet, I need to find out why it's wet.